Hey everyone, my name is Lydia, and this is what I wish they had taught me about econometrics and introduction. In this video, we're going to finally dive into the deriving of the OLS formula in matrix form. Keep in mind, I know very well that you have a lot of resources and materials out there that show you the step-by-step procedure and also the final formula. However, what it might not be clear are sometimes a few steps that are either omitted because you are believed to already know these facts or simply because the final answer is more important than the actual steps. So with that in mind, in this video, we're going to go through those little tricks that have been used in order to get to the final answer that you have on your OLS matrix formula. We will start the model as usual from our y being x beta plus the error term. Keep in mind the x here is a matrix and the beta here is a vector of all the betas that you are going to estimate, including the beta null. As usual, the concept behind the OLS does not change. The OLS minimizes the sum of the squared residuals. Most of you might have seen this expression, however, you will probably not have thought of or have not asked yourself why and where is this expression coming from. So if we are talking about the sum of squared residuals, we know that the residual itself is the difference between the actual observed value and the predicted value. And keep in mind, when we have the predicted value, the y hat in the matrix form, that means that you have estimated all of your betas in here. Of course, me putting the beta hat, it's not the same as in the scalar version, because here again, we're talking about a vector of all of the betas. But keep in mind, what I'm saying is that for all of the betas in that vector, meaning beta null, beta 1, and so on, I have an exact number that I am estimating the moment that I am done with this process. So, keeping in mind that the residual is simply the difference between the true y and the estimated results, we are going to write in here the epsilon simply as, so the epsilon hat simply as y minus x beta. But it's the sum of the squared residuals, right? So why do we need to write it twice like that? Well, keep in mind, we're working in the world of matrices, right? So this residual term that we will get ultimately is a vector that goes from E1, E2, and then n here. So as you can see, the dimensions of this vector would be n times 1, or as we call a column vector. Now, if you have to multiply this residual vector with itself here, so imagine that you had another E1, En, this multiplication in the matrix form is not possible. So what do we have to do to make sure that we can actually do this multiplication? Well, if the first one is actually transposed, then its dimensions, so if we have the first one transposed, then its dimensions will match the ones of the residual vector, and we will be able to then do the actual multiplication, because technically now this has dimensions 1n, while this has dimensions n times 1. So ultimately, we're just going to have a scalar number that is the residual square, okay? So again, reason for this prime in here, which is just the transpose, is to make sure that we are matching all the rules in terms of matrix manipulations and operations run with them. Now that we know the whole principle behind this, let's continue with the next proof. For a lot of you, it might be difficult to jump from this minimization problem, which sometimes you might even see very shortly written as this, instead of having the entire expression in terms of the y and the x matrix. And most of the times, you jump directly to the derivatives. But how do we get from that minimization problem to the actual derivatives? There is a very specific identity that is used in order to get to that stage. And the identity is A minus B transpose times A minus B is equal to A transpose A minus 2A transpose B plus B transpose B. This is matrix world. We will have another video where we explain all of the properties that you will need to know about operations with matrices. But for now, let's take this identity as given and keep in mind this is exactly what we're now going to use to expand this function that we have right here. So using the formula, the function very easily becomes as y transpose y minus 2 beta transpose x transpose y plus beta transpose x beta. Okay? So this is the final formula, and this is the trick that it's used to get to an expression that now might be a lot more easier to find its derivative of. There are, in any case, a few more reminders that I will put in here before we move to the derivative bit. And it's again those little math elements that most of the times you're taken for granted to know. And these are just matrix calculus facts, if you want to call them that way. So just keep them in mind. The first reminder is related to a matrix calculus fact that says that the derivative of this expression with respect to the beta, or of this following expression, so beta transpose a whatever matrix A times the beta vector is equal to simply the A matrix plus the transpose of it times beta. Okay? Now, if A is symmetric, then the entire expression is actually equivalent to 2A beta. And the last matrix calculus facts that we are going to use is if we have to find the derivative, again, with respect to B of an expression that is C transpose B, this is simply going to be C. Okay? One more. These are reminders on, as I said, matrix calculus facts. Another element that we are going to use so that we do all of the manipulations when we look at the derivatives is the fact that X transpose X in our case is symmetric. Now let's find the derivatives. The derivative of this expression with respect to the beta, so we only look into this expression and to this expression. This was also the reason why we needed to go through these two reminders, because these two expressions are very similar to these two rules that we just put out there. The derivative will be simply 2 times x transpose y plus 2x transpose x beta. Because this is a derivative, the first order condition, we can equal it to 0, rearrange it in order to get that the x transpose xb is equal to x transpose y. Keep in mind, the transposes in here are always to make sure that whenever you're doing a multiplication, the dimensions are matching. This expression that you get in here is also what we call a normal equation. Okay, and you can add s in here instead of just normal equations, because as a reminder, the beta in here, it's a vector of all your betas, including the beta null. That's why in here, we're not going to have to separate videos on showing you the beta null and then the other betas. It's all calculated at the same time. The way that we solve for beta in here, we have to add a very important fact that needs to be fulfilled. and that is now that the X transpose X is actually invertible. If this matrix multiplication in here product is invertible, then we can rewrite the beta solution, so our beta hat, exactly as X prime X, so the inverse X transpose Y. Okay, so as you can see, the entire OLS formula here collapses into just one little line. You don't have the summation notations or any other algebra. You don't have separate equations for beta null and beta 1, because remember, these beta hat in here, it's still a vector of all of your betas, including the beta null. Okay, now some little things in terms of like interpretation before we finalize this video. One thing that you have to keep in mind as this X prime X product comes very often into our expression, remember that this product actually captures the geometry of the regressors, the X transpose Y. This is what captures how the regressors relate to Y, and the solution is a projection, which means that just as we wrote in the previous video where we had that the projection was P times Y, in this particular case, we have the projection, so the fitted value Y hat is equal to matrix X here times beta hat. Okay? This is exactly the projection, again, of Y onto the column space of X. This makes also a little bit the connection on the previous videos that we've had on the geometry of the matrix notation of the OLS. This representation is why Green or other advanced econometrics books rely so much on matrix notation. And now you know both versions, the scalar OLS formula and the matrix OLS formula. Soon we'll build on this to explore the different properties of the OLS and also multivariate regression and projection geometry. So I'll see you in the next videos.